Hi, I'm Mike Seaman for Eta Power. In this video, I'll show you how you can add your own device models to your Eta Designer projects. We'll start with a simple closed-loop buck converter. While the converter simulates fine, we need to add accurate device models to calculate efficiency. The power transistor and inductor we'd like to use aren't in the master library, so we'll have to add them ourselves. To start, we'll open the library manager. Since we can't add models to the master library, we'll have to create our own user library, and we'll just call it userlib. Now that I've created a user library, let's add a transistor. We'll start by adding the CSD18534 transistor from Texas Instruments. So I'll click here for plus and type in a short name to describe the transistor. This has to be unique and is used to identify the device. So I'll just call it CSD18534. Okay, so we'll choose the manufacturer, and I already have Texas Instruments here. If you don't have the correct manufacturer here, you can add that in the manufacturer's view in the database window. The next step is to type in the full part number and the datasheet. So we'll go over and take a look at our datasheet. And then we can type in the full part number, or copy and paste the full part number into the window. And finally, we'll copy and paste the URL. Let's see. We'll then select the package for this part, and we'll call it a TDFN 5x6. And if that doesn't exist, we can add that to the semiconductor package category as well. So then we'll fill out these values from the datasheet, the on-state resistance, maximum drain source voltage, and so forth. So let's take a look at what those are. We'll come down here and find our on-state resistance category. So that's here. We'll look at it with a 10 volt gate voltage. So typically 7.8 milliohms and max of 9.8. So we'll add that in. So typical is 7.8 milli, so don't forget the milli suffix there, otherwise you'll be 1,000 times too high. So this is a 60 volt part with a maximum temperature of 150 degrees C. So I'll type that in here. We'll look at the threshold voltage, and that's right here, typically 1.9 volts. We'll continue on and type in the rest of the numbers here from the table. So the next step is to look at transconductance, and that's taken as a certain current. So it's 72 Siemens at 14 amps. So we can type that in here, 72 Siemens at 14 amps. And then we'll look at the diode conduction mode. So we'll come down here. Diode is 0.84 volts at 14 amps. So we'll type 14 amps here and 0.8 volts there. Now let's look at the recovery. So this is taken at 14 amps, 300 amps per microsecond. It's 54 nanocoulombs and 40 nanoseconds. So we'll type in 40 nanoseconds, 54 nanocoulombs, a drain current of 14 amps, and 300 amps per microsecond, or 300 megamps per second. So that's all set there. The next step is to define these curves. So let's start at the top one. This is the on-state resistance temperature coefficient. Here's the curve for the on-state resistance of the part as a function of temperature. So what we'll do is actually just copy and paste this curve into that window. So let me do a screen capture. And capture this graph. I'll copy this graph, come over here, and since this is normalized, I'll click the relative box here, define the part, then we can paste the image right into the window. We see that the x-axis and the y-axis are linear, so these settings are correct, and we can hit the next button. Now what we want to do is define the axis. So I'll follow the prompt here and click on the origin. And then type in the values here. So we're minus 75C and 0.4. Next, I'll click on the the rightmost tick on the x-axis, type in 175C, then click on the y-axis, and that's a value of 2.2. So next I'll click Add New, click a few times on the curve, like that, and now I can click Preview and see that it's extrapolated temperature coefficient from this line. So that's all we need to do for this plot. I'll click OK, and now the buttons shift to Redefine to indicate that we already have some data there. Next, I'll click on the buttons for the output and reverse capacitance, the gate source charge, and the gate or the RDS on versus gate voltage curves, and fill those out respectively. For this graph, we want to capture both the output and the reverse capacitance. We see that we actually have a linear axis here and a logarithmic axis on the y-axis, so we'll set the scale accordingly. So I'll click Next. I'll go through the same steps of clicking on the origin. Here we'll type in 10 picofarad for the y-axis value. It goes up to 60 volts here. Volts. And 10,000 picofarad or 10 nanofarad on the y-axis up here. So next we'll click Add New, and now I want to choose the capacitance for which I'll add data. So I'll just start with COSS. Click OK, then click a few points, enough points to define this curve on the plot here. And I'll click Add New and repeat the steps for the reverse capacitance. I'll click Preview and see that both curves have data on them. For the red one, it's hard to see because it's already a red curve. So I'll click OK, go back to our window, and see that that one's already defined. So I'll repeat the steps for the final two pieces of data. So for this graph, what we'll do is look at the room temperature data and click along those points. Some data sheets don't have this graph included, so it's okay to actually omit this data. The Eta Designer will use the GM to extrapolate this data based on the threshold voltage, but it's always more accurate to copy it directly from the graph. So now we have all of our data defined, and we can click OK, and it will be entered into our database right here. Now we can define an inductor. So here we're going to choose the Coilcraft XAL6060-822 part. So I'll type a short name, XAL6060_822. And that's a short name for the part. I have Coilcraft in here, it's already selected. I'll type in the full part number here. 6060-822, ME is the suffix. And now what I'll do is I'll copy in the data sheet. So I have it open already. Right here, I can copy this and then paste that right here. So the package is something I'll have to define in just a second, so let me leave it blank for now. It's going to be a shielded ferrite part with a typical inductance of 8.2 microhenry. So let's find out the tolerance. 20% tolerance. Typical DCR is 24 milliohms. 24 milliohms. So the self-resonant frequency of the part is 16 megahertz. 16 meg. Now we're going to look at the maximum thermal current. So that'll be, we can have a choice of either 20 degrees C or 40 degrees C. I'll type in the value for 20 degrees C, and that will be 6 amps. So now we have to enter in two sets of plots, essentially. The first one is going to be inductance versus DC current. And here's our plot right here, 8.2. 8.2 microhenries. So we'll copy that, paste it here. It's linear and linear, so we're good to proceed. Click here, click at the origin, and that's 0, 0. Have 10 amps here, and then the plot goes up to 12 microhenry. So now what I'll do is just click on a few points along the graph to capture the saturation of this inductor. And that's going to be good enough right there. Now we'll define core loss. So this is actually a little bit different. We don't enter in a plot here, but we have to enter in data points of frequency, peak-to-peak current, and the corresponding core loss. Hint, some data points we can enter. I hit suggest points, and then there's 6 points we can fill in. So what we're going to use is the manufacturer's data on their website. Enter in these parameters and copy in the resulting core loss. So we'll start with 150 kilohertz. Define an average current of 4 amps through the device, and then a peak current of, what am I looking for? 5.5 amps, peak to peak. So I'll type that in here, 5.5. We have our inductor here, click compare. And out comes our data. So we'll take a look at the total losses and see that our core loss, core plus AC winding loss, is 777 milliwatts. So I can type that in here. Now what we're going to do is go through the remaining 5 points and get all that data. Now that I've entered in all the data, I can click OK, and Eta Designer will perform a curve fit and enter that data into the model. So I'll click OK here. Now let's go and define the correct package for that part. So what I'll go to is passive packages. I'll click new here and enter in that XAL6060 part. This will be a generic part for all of those entire series of inductors. It'll only apply to inductors, and it'll only apply to coilcraft parts. So we'll go back to the data sheet and look at the physical dimensions of this part. So we see it's 6.6 millimeters wide, 6.4 long, with a height of 6.1 millimeters. So I'll enter in that data here. So 6.6, 6.4, maybe minimum of 6 and 6.4, something like that. Thermal resistance to ambient is going to take a little bit of calculation, but we can see that from our performance back over here. So we see that our part has 1074 milliwatts of loss with a temperature rise of 28 degrees C. If you divide the two, you can see that we get about 26 degrees C per watt thermal resistance. For an inductor, lead inductance doesn't matter too much. 1 nanohenry should be fine. So click OK. Now we can go back to our inductors, edit this inductor, and choose the correct package. So here you see our XAL6060 shows up. Click OK. The database will automatically update and it saves automatically. So now what we'll do is set these devices to be the models we just defined. So what I'll do is click on Library, Convert to Library Component. Once I do that, it'll open a dialog to allow me to choose a part number. So I'll click on that, and right now there's a filter in here that sets the maximum drain voltage. So we're looking at 60 volt parts, so I'll type that in, and here is our CSD 18534. So I'll click on that, and that defines that part. We can do the same for this part down here. And now we can do the same for the inductor. All right, so just like that, we've now defined our custom models for our 2 transistors and our inductor. And now we can simulate efficiency and find out how these perform in our circuit. Thanks for your attention. Please check us out at etadesigner.com, where you can download a trial of our Power electronics optimization program, Eta Designer.